Okay, thanks everybody. And today we will talk about the integrated sensing and communication for 6G. So we will discuss several topics. And thanks for the National Science Foundation. So here's the outline. First, we have the motivation for integrated sensing and communication. What is the foundation? What is the waveform? And what is the performance trade-off? And then we talk about the applications like the waveform design, multi-user resource allocation, this kind of physical layer security attack, high-speed train, and even optic. And finally, we have some kind of prototype demo and standardization and conclusion and future works. So for integrated sensing and communication, so basically it's try to integrate the communication and the radar. And this is two different type of applications in wireless. And now wireless spectrum resources is very limited. So how could we share them? And so that, okay, we can save all these things together. So we have the massive communication and sensing demand, and also with limited spectrum resources. So for the ESAC, it's basically, okay, it's try to do the communication in the front, in the communication side, in the forward, and because the receiver will reflect the signal back, so we can do this kind of sensing in the backward. And the ESAC is one of the 6 ITU usage in the future 6G. So for ITU 6G, typically we have 6 different one. 3 come from this 5G, and 2 or 3 new from the 6G, and the 3 new 6G is the AI and ubiquitous communication, which is the space, ground, air kind of integration, and finally is the ESAC. Okay, and the ESAC have many kind of application usage. First, about the autonomous vehicle. You know that, okay, Elon Musk first say, okay, only the stupid people using the LiDAR. And at that time is right, in the sense that, okay, if you use the LiDAR, even though they can see a lot of new things, who will train it? Who gives them the kind of training sequence? Because for us, when we drive a Tesla car, every time we drive, we are the training sequence for this for Tesla. So they don't need the people to label it, right? And now after millions of miles, and for these millions of people, they get the training sequence, they got the self-driving. Now, in order to go beyond this kind of visual one, they can equip back this LiDAR again. Okay, so in this case, okay, nowadays after they get the trained for the full FSD, he begin to adopt the LiDAR again. So this is the reason for that. And currently, we are working with Ohio University and Purdue University for this extended reality. So basically, okay, if we know the location, and then in the future I have this XR glass, then okay, I can tell, okay, I can have virtual things here. And for XR, you need to 6 dimension. Your height location, which is 3 dimension, and your XYZ. Your XYZ location for outdoor is okay, because you can use the GPS, but indoor is a problem. If your indoor localization is not good enough, then you cannot locate this your height and view direction correctly. Then your XR will not kind of put in the wrong place, right? So this is the case. And the surveillance service and surveillance, my PhD advisor got the National Academy of Engineering, and last year, and his company doing this kind of surveillance, secure surveillance. By the way, this one will be on my website, and security. And so basically, they're using the Wi-Fi to detect this kind of people to enter the house, enter the window, or even your sleeping pattern, or falling. If the old senior people and fall, they can detect it. And obviously for industrial 4.0, okay, that is Internet thing, is definitely application. And the industrial 1.0, 2.0, 3.0, 4.0, now we have the communication and all this kind of upgrade for that. They need the exact location for this one. So indoor, especially this robot, okay, if they can know exactly the location, they can get it, especially with RFID, okay, and how could locate the things. And nowadays, okay, those RFID is so amazing. Now you buy some kind of thing from Amazon, half days is delivered to your apartment. You can even track it, right? How come? They have RFID and localization there. Okay, and this is my PhD student. He will go to Mars, and I mean for him, and then okay, before he go to the Mars, he need to finish the paper. Okay, anyway, and then some other applications like this entertainment, maritime, public safety, and disaster, and so on. So this is the kind of things, and in history, okay, this I mean ESAC first started from the dual function radar communication DFRC by designing the signal and system capable of fielding both radar and communication simultaneously, and DFRC achieves significant resource efficient. And the DFRC is a waveform design, MIMO, signal, hardware, and coding, modulation, and resource allocation together. And so typically, okay, they have the hardware gain. So basically, okay, they can using the same spectrum, same hardware to do the both function, but they have the trade-off. And they can scale the trade-off. So basically, okay, they want to design this kind of efficient of this DFRC so that they can pay attention to radar more or pay attention to the communication more. And also because the spectrum, our original radar and communication are using a different spectrum. Now they're using the simultaneously. So basically it's more efficient, but also increase the complexity and also the interference. Moreover, okay, we need some kind of more standardization and regulation to for these type of things. And then compare with, I mean, traditional DFRC and ESAC. The ESAC, DFRC is a subset of ESAC, focusing on shared waveform antenna and processing for radar and communication in a shared hardware. And ESAC can use other devices separately. So in other words, DFRC basically, okay, I'm the transmitter to their, and also I'm the receiver. So basically, okay, I'm under the transmitter and the receiver. I'm doing the ESAC for communication. Let me go back a little bit. This is more obvious. So DRFC, okay, my transmitter and the receiver will be the my communication and the receiver and the sensing, okay, will be the same receiver. And for the ESAC, okay, my receiver for sensing can be a different one. In other words, my base station sensing, for example, okay, some student here, Dr. Pan here. Where is Dr. Pan? And then my student devices, instead of base station receive the signal for the sensing. Maybe you know that for sensing, okay, some of the student phone can receive it. So the receiver of sensing might be different from the transmitter of the sensing. So that is a major difference between the DFRC and the ESAC. Obviously, the transmitter and receiver for sensing can be the same. And in this case, okay, that is DRFC. But if they can be different, then that is ESAC. So the major thing is that, okay, for the DRFC, they require this shared waveform, shared hardware. So basically transmitter and receiver is the same place. And for ESAC, okay, they can separate hardware. So the receiver can be differently. And then, okay, there are some kind of different application and different waveform design. And then, okay, for waveform, okay, they can have different. First, for Wi-Fi 4G, 5G, 6G, they have the OFDM, which is very matured. And so basically, subcarrier can be used for the radar sensing and communication simultaneously. However, okay, this is in this kind of time frequency domain. However, okay, for OFDM, the major thing is that, okay, if you have Doppler effect, then okay, your subcarrier sampling, I mean your timing is not good. Sorry, it's not timing. Your frequency kind of synchronization is not good. Then in this case, okay, your carrier recovery might not be good. So that okay, you are not in frequency domain. You are not sampling at the peak of this OFDM part. Then in this case, you will have the inter-subcarrier interference, right? Remember, only at the sampling frequency, OFDM is kind of orthogonal to each other for the different thing. If you are slightly different, you will have the you will have the inter-subcarrier interference. So in this case, OFDM is only work for this low frequency part. And for example, if you go to this high-speed train, and then your I don't know nowadays before COVID, okay, if I'm using my phone in the high-speed train, I mean when the speed is high, I cannot have this receive signal due to this subcarrier problem, synchronization problem. And for OTFS is delayed Doppler in the delayed Doppler domain. So basically, they're using the 2D inverse symplectic Fourier transform to transform this kind of I mean, from the time frequency domain to delayed Doppler domain. So in this case, okay, they are very good at this kind of high speed one. In this case, think about delayed Doppler. What is a delayed Doppler? Delay is basically the distance, right? And the Doppler is a different speed. So think about the space, this kind of Starlink and the ground one. For ground one, you are not moving too much. The speed is low, right? So in this case, okay, the Doppler is low. And then, okay, the delay, you are not too far away from the base station, just a few miles at most. So this delay is short. And on the other hand, in the space, okay, all this kind of is at least 550 kilometers above. So the delay is long. And also the speed, that is a kind of, I mean, 1 second, 14 kilometers per hour, right? So basically, okay, the speed is high, so the Doppler will be high. So in this case, okay, even though they are using the same resources, the delayed Doppler kind of location is very separate. So that's motivate us that we can do the resource allocation. We can try to reuse the spectrum together. And so this is a different, but unfortunately, okay, for OTFS, they're using the ISFFT, which is a square wave. And we know that, okay, for square wave, the pulse shape is a square. So in this, if it's square, in the other domain, it's kind of sinc function, right? The sinc function will have very bad kind of side lobe. So in this case, okay, even though that, okay, for delayed Doppler, okay, the story I mentioned is very ideal. But if you're using the OTFS, then okay, this side lobe interference will be everywhere in the delayed Doppler domain. You cannot have too much kind of resource allocation because when user is there, the leakage will be everywhere. Yeah, so that's reason, okay, recently people using the ODDM, using the orthogonal-based function to design this kind of, maintain the orthogonal in the delayed Doppler domain. But obviously, okay, the complexity will be high and also is less mature because they have a different design for that. So that's reason, okay, this is the kind of development. OFDM, widely used, but low frequency. OTFS, well, I mean, it's a straightforward development, but too much side lobe. It work for the, I mean, delayed Doppler domain. But the ODDM, I mean, is still premature, and also the complexity is high. So this is basically kind of a comparison. And also for this OTFS can introduce a leakage problem, and also because they also have the peak to average ratio like OFDM, and but it's really simple implementation. But the ODDM is on the orthogonal pulse specific designed for ESAC and in the delayed Doppler domain. And it's good for the multi-user case, but still early research. So this is a kind of comparison for those. Okay, there are some kind of fundamental trade-off. So for radar and for this for this kind of communication, so basically this is a two objective function. And when you have a two objective function, okay, if you try to satisfy one thing, the other thing will sacrifice. So in this case, okay, we typically have some kind of a Pareto optimality. The so-called Pareto optimality means, okay, if I want to increase one objective function, the other objective function have to suffer. So you always have this trade-off. And this trade-off appear everywhere from the spectrum, signal design, power, time resources, spatial resources, interference, and so on. So I listed all those things. Okay, due to the time limitation, okay, maybe you can go through it. But fundamentally, okay, the result trade-off is the Pareto optimality. You have two objective functions you have to consider, and later we will show you how to balance these two objective functions. Anyway, so this is a kind of a background about this ESAC. And honestly speaking, I found this this direction changing very quick. I'm also in a starting curve. So let's go to this application. Okay, so the first one is OFDM resource allocation, and this is published by JSAC last year. And so basically, we try to satisfy the diverse requirement of communication and sensing, and we design the dual function tend to be allocated the different resources element. And the resource element is conducted in the time domain, power, delay, Doppler domain to enhance this both peak to average, peak to side lobe ratio, and achieving the data rate. So basically, this is a block diagram. And so here, okay, we try to balance between this peak to side lobe ratio and this achieved data rate. So here, the thing is that, okay, we define this sensing metric with peak to side lobe ratio. So here is a signal performance matrix. Here, the signal matrix. S is signal on the K subcarrier of OFDM, and the U is allocated communication and sensing. And so for performance metric, okay, this one is here also some power constraint and so on. Here for communication, this is the overall data rate for the different subcarrier, and the sensing is a peak to in the region of interest in the delay Doppler domain. So basically, okay, peak to side lobe ratio. So basically, okay, in the delay Doppler domain, okay, how my signal, okay, will look like. So for the sensing, focus on this delay Doppler domain, improving the peak to side lobe ratio of a region of interest, where the communication focusing on the time frequency domain. And communication concentrate waveform are then the resources with good channel. So in the communication centric, okay, I will allocate this channel, allocate the channel with a good performance, water filling, right? Remember water filling, right? It's a nightmare last semester, right? And then, okay, for sensing-centric waveform, it's guaranteed the perfect autocorrelation property with a region of interest, then optimize their delay Doppler domain value to improve this achieved data rate. So the so-called, I think the so-called this kind of peak to side lobe ratio is the energy that I concentrated with the region of interest over the side lobe. That means how concentrated my energy it is in the delay Doppler domain. If I'm concentrated energy, if my energy is very concentrated, my PSLR is high. That means, okay, my lens is very sharp in this kind of a delay Doppler domain. I can detect it very clear. Because if my peak, the energy inside and the energy outside is low, the PLSR is low, my lens is not unfocused, right? Most of my energy is outside, it's blurred everywhere. I'm not clear. So this is the reason, okay, to design it. And here is a kind of thing. So this is a region of interest. I want to concentrate my energy sharply into inside my region of interest. Outside, I want to have some kind of less energy into it. So in this case, okay, in my sensing in the delay Doppler domain is very sharp. But on the other hand, my communication on this achieve the data rate, and then okay, will be kind of in time frequency domain will be high. So this is basically kind of trade-off. Okay, so this is a kind of waveform design, and you can see many kind of waveform design kind of paper, just like what I mentioned. OTFS is just a very straightforward by changing the OFDM over this kind of certain Fourier transform. But for ODDM, you have to design a kind of waveform. This is one way to design the waveform. You will see thousands of papers design different waveform with a different kind of objective function and constraint. And now, okay, we want to have the multi-user resource allocation. So basically, okay, what we want is that, okay, we want to squeeze the user. For example, the people in a low speed and people in the high speed. And I think we should put a starting kind of user here instead. Okay. Anyway, so here we have this time domain. This is a time domain discrete sample of the ODDM signal, the receive signal domain, and this is a kind of a parameter for ODDM. And then okay, we have the signal to noise ratio. This is a on the left hand side is a communication. Is basically capacity. On the right-hand side, we are trying to sensing this kind of Kramer lower bound. For sensing, okay, for any unbiased estimator, next method, okay, do not forget to select my courses. This method, okay, 6333, okay, estimation detection. That is very useful, very useful courses, okay. And so basically, okay, for any unbiased estimator, I mean, it will be bounded by the Kramer lower bound. That means the performance, the variance will be bounded. So if we can calculate this kind of Kramer lower bound, that can be a kind of performance on how much kind of estimation we have. It's just like, okay, the so-called, I'm trying to estimate where Dr. Pan is. And then, okay, I have a Kramer lower bound as a lower bound for the variance. So basically, okay, maybe it's here, maybe it's here. So I have a variance to estimate. And then if we can bound it on the Kramer lower bound, then okay, we can use this Kramer lower bound as a sensing kind of performance. And this is a communication line. And then now they have this kind of a Pareto optimal. So basically, this is the Kramer lower bound. This is a ratio on this figure. And you see on this kind of blue curve. And this is a kind of, I mean, Pareto optimal point. If we want to increase this kind of overall rate, my Kramer lower bound must increase. That means my sensing performance will drop. And on the other hand, if I want to improve the sensing performance by decreasing the Kramer lower bound, my kind of data rate, okay, will drop. So this is a trade-off I mentioned, I mean, before the application. So this one, the key question is that, okay, how could we obtain this kind of Kramer lower bound? And here we can using some kind of, we try to combine this, this Kramer lower bound plus mu times of rate. So this is become a linear, right? It's a linear line. And then we try to, please, online, please mute, okay. Mute, okay. Let me see. Okay. And then, okay, by selecting one mu, I have one line here. And for the problem formulation that I put here, I will get the optimal solution here, right? And then by changing to another mu, by changing to another mu, then okay, by changing to another mu, I can find the point over this Pareto optimum. So by sweeping this mu, I get this Pareto optimal point. So this is how the solution is coming from. And here, okay, there are some simulation results. On the left-hand side and right-hand side, we have the comparison with the OTTM and OFDM and ODDM. You see OTFS. You see the OTFS, okay. We using the same scale. You see the side lobe, even though we have just a few users, and then, okay, the side lobe is relatively high. They are interfering with each other because they're using this kind of square wave for this very straightforward of Fourier transform to change from the time frequency domain into the delay Doppler domain. So the side lobe is big. But by using the ODDM, okay, the side lobe will be smaller so that we can squeeze more users into it. And obviously, in this case, okay, for the delay, for this kind of Kramer lower bound and rate for Pareto optimal point, we are much better. With the same kind of sensing performance, we can have the better data rate. with the same rate, we can have a smaller criminal bond, better sensing performance, because for ODDM, we have the less interference with each other. Okay, so this is basically, okay, the second work. And the third work is a kind of disco. So basically, okay, let me see my time. Wow, it's a bit quicker than I expected. The third work is the integrated sensing and communication using the dual function transmission form. And so basically, okay, this is a receive signal, and how to design a E-cyc waveform such that, okay, we can improve the signal to noise ratio while also kind of improving the sensing one. So this is a kind of things. And also by adding this kind of reconfigurable intelligence service, then we have the extra multipath. And so in this case, okay, we can improve the performance. And this is a E-cyc based aided kind of E-cyc performance. So basically, okay. Also, we can design this active beam filming and passive beam filming to improve the overall performance by knowing that by having the extra path for this. So this is a kind of optimization. And here, what they do is that, okay. Let me see, remember. So here, what this paper proposes, we have the disco reconfigurable interference service. And then, okay, so, okay, this is a disco, okay. Let me say how to interpret. Here we try to using this RIS to improve improve the physical layer security. The reason is that, okay, for physical layer security, the problem is that, okay, I don't know where the location of my eavesdropper, right? So I really don't know. And then in this case, okay, this is Achilles heel for this physical layer security. And then, okay, what the disco means here is that, okay, for RRS, if I know this kind of, the eavesdropper's location, I can either jamming that eavesdropper, or I can reflect the signal to the source one to improve it. But currently, I have no idea about where eavesdropper. So what I can do is that, okay, I'm using the RS as a disco. You go to the disco club, and then when you look up, there's something rotating, right? So basically, okay, rotating to all the different direction, and that one will kind of make your eye glad, right? So basically, okay, you cannot see in the disco place, especially nowadays, all laser. Last time I was in Glocom last year, and then on the reception they have this laser one. Nobody can see each other at all. Yeah, so this is a kind of disco kind of jamming. Okay, and then in this case, okay, they have proved that, okay, by this random kind of jamming, they can improve the performance. Okay, so here the question is that, okay, we are trying to using this disco to change this to add this kind of jamming channel, and then we have this receive signal for that, and then, okay, could we control this kind of jamming such as, okay, control the power of the jamming so that we can improve this sensing, and we can degrade the sensing and for this eavesdropper. Okay, and here are some kind of performance result, and I think on the left hand side is overall data rate. On the X is jamming, and on this one is data rate and jamming. I think I need to improve this application. I need to improve a little bit. Okay, and this is this is improve the performance, and then this is a kind of try to design this receive communication and sensing matrix. This is a communication and this is sensing, and then, okay, they try to design the trade-off, rho plus 1 minus rho, basically changing this. You can consider, if you divide rho here, that is mu that I used using the previous example. This is the power constraint. The first one is the first one is this communication metric. The second one is this sensing metric. So by changing the mu, basically you're changing this line, you find this Pareto optimal point for this. And then, okay, here is certain kind of result in the middle. Okay, how could you change this kind of result in it? So I think I can quickly skip it. And here is the sum rate. Okay. This is a different antenna component, and this is transmission power, and this is the overall power. I think I need to upgrade this side of the slide, but it's okay. Okay, and so this is the third application, and the fourth application is a high-speed train. So for high-speed train, as I mentioned, okay, for high-speed train, okay, if you don't know this kind of, I mean, if you have a high delayed Doppler kind of effect, and the communication will kind of, communication performance will be degraded if you're using OFDM. And here, the ESAC, intelligent high-speed read, require a new integrated sensing communication to balance two functions: optimization, resource integration, enhance the communication and data rate, improve the accuracy of the environment sensing, and meeting the demand for this. So why this kind of high-speed train need? Because for high-speed train, they have the base station nearby, and if they know the train location, and if the localization good, they can do the beamforming toward this kind of train, high-speed train, in a very accurate way. So in this case, okay, ESAC is also important to provide this communication for the customer on the high-speed train. Okay, and here this is example the speed train moving the base station using the ESAC to locate the location of the customer. So we have the ESAC base station, mobile relay, and we can also have the eavesdropper and so on. So basically, we have the parameter by changing the beamforming pattern and also the waveform design matrix X. And here we want to, I think we need to remove the eavesdropper detection. Okay. And here we want to maximize, the problem one is we want to maximize the overall capacity rate under the transmission power, under the constraint of modulation constant, and also the sensing requirement. So this is a sensing requirement, and this is one region constraint. Okay, so basically they want to maximize the capacity. Here the sensing is the requirement, so that it's in the constraint, so that they know where this beamforming location. But on the other hand, okay, they want to maximize the overall data rate. And such kind of problem can be decoupled. And so basically, okay, they found the lower bound for the objective function, and then they have the constraint relaxation. And after that, they decouple the variable, and then they put the different optimization problem. They do the iterative until the convergence. And here they have this result for this Kramer lower bound, and this data rate, and this is the proposed algorithm. This is a victim algorithm. And on the left-hand side is this kind of transmission power, and then this is a legitimate user rate with sensing kind of requirement. Okay, so this is a high-speed train. And finally, okay, for optical, for free optical, free optical things, communication is like a LiDAR and some other things, is also a kind of 6G communication. And moreover, for Starlink 3, okay, currently they just sent up. And before that, they're using this millimeter wave for this inter-satellite communication. But now they're using this free optic, so basically laser, to between this kind of two satellite. So in this case, okay, the communication will be higher. And also, okay, for example, for this Wi-Fi communication, And for this Wi-Fi communication, they can put this light. They can put a light for communication. As long as you can see the light, you can communicate. Instead of using Wi-Fi, you're using the Wi-Fi. Okay, and also LiDAR communication. Yeah, just like the example I mentioned for the Elon Musk communication and this localization is also important. So basically, okay, the research gap is that, okay, most of this kind of free space optic ESAC focus on this single carrier waveform, or the OFDM. And what is the optimal DC bias for intended modulation and direct detection, IMID-based signal? Okay, and here the contribution is that, okay, they designed the direct current biased OFDM and scheme to improve this performance. They have the joint optimization for the DC bias and subcarrier power for the communication performance under the constraint of the sensing performance and power constraint and some kind of other physical constraints for the LiDAR system. And here is this trade-off for this spectrum efficiency or capacity, and this is a kind of a procedure. And then, okay, and so basically, okay, this is their result. Okay, and finally, we have this prototype demo and standardization. So for the first prototype, we're using the reconfigurable holograph surface-aided ESAC. So this is a holograph kind of leaky wave antenna, which can control on and off for this window so that they can do the beamforming. And in this case, it's called a reconfigurable holograph surface. And so in this case, they are trying to do the sensing and localization. This is sensing the direction. And then this is the communication data rate. And then they also do this kind of target moving indoor and outdoor. And so basically this is the estimated range and the direction. So basically, okay, they can track these things correctly. And this is a demo that we show in the MUCOM in the last December.
Integrated Sensing and Communication ISAC is a groundbreaking technology that merges sensing functions like tracking, activity recognition, and medical imaging with communication services such as email, texting, and video transfer into an integrated framework. Looking ahead, ISAC plays a crucial role in 6G networks by improving efficiency and reducing latency. Aligned with GMT20250110 and 6G, ISAC drives next-generation mobile technologies. A key aspect of ISAC is transitioning from traditional radar communication coexistence system to dual-function radar communication systems, which enables cooperation instead of resource competition. Moreover, ISAC allows for flexible optimization between radar and communication functions by joint waveform designs, where the waveform, like orthogonal frequency, divides in multiplexing OFDM and orthogonal time-space frequency OTFS are used for detection and information. In this demonstration, we showcase the practical implementation of a multi-waveform ISAC system, which integrates radar sensing and communication seamlessly. This setup allows for real-time object tracking and data transmission over shared wireless resources. The monostatic radar platform includes a USRP for signal transmission and reception, an up-and-down converter to shift signals between baseband and high frequencies, and beamformer transceivers to improve detection accuracy by directing radar beams towards specific targets. The communication receiver includes a USRP to capture transmitted signals for processing, an up-and-down converter to manage frequency shifting for efficient transmission and reception, and a horn antenna to enhance signal reception and transmission.
This demonstration features an ISAC transmitter and receiver that transmit data packets containing a preamble, guard interval, and pilot bits. At the receiver, we evaluate both the user's position tracking and the communication throughput. The ZAC-OFS waveform, recognized for its robustness in dynamic environments, is utilized to facilitate simultaneous sensing and communication. The experimental setup is depicted in the top section. In the bottom section, the receiver's tracking of the user's movement is visualized on the left, while the communication throughput performance is shown on the right.
We then compare the performance of the ISAC model with OFDM and multi-carrier OTFS to highlight the advantages of each waveform. Here we compare OFDM, MCOTFS, and ZAC-OTFS waveforms in terms of spectral efficiency, mobility support, multipath handling, complexity, standardization, and application scenarios, highlighting their trade-offs and suitability for different communication environments. In conclusion, the ISAC-OTFS system successfully demonstrated its ability to seamlessly support simultaneous object tracking and communication. By leveraging the ZAC-OTFS waveform, the system maintained high accuracy even with user movement. ISAC-OTFS systems paved the way for research in adaptive waveforms like orthogonal delayed Doppler multiplexing ODDM and resource management strategies. These advances are crucial for applications in autonomous vehicles, healthcare, and smart cities. Integrated.
Okay, and let's see the demo and with Purdue and Princeton University. And here, this is the ESAC timeline. So over the years, okay, they have this kind of early research, pre-standard, standardization, proprietization, formal standard, and so on. So basically, okay, you can see the timeline is still a kind of a developing area. So this is a kind of one of the major 6G development. And the conclusion is that, okay, it's a potential to transform industry and enable wide range of application for sensing and communication. And also ESAC is need to carefully design this waveform, beamforming, resource allocation, and hardware. So it's a very cross-disciplinary research. And well, on the other hand, my comment, you need to find a killer application, not like AI. AI is everywhere, right? So it's obvious. For the ubiquitous communication, which is space, air, ground, and all this UAV and Starlink, you can obviously see this one. Nowadays in our Los Angeles, okay, you get a free Starlink connection, right? It's due to the wildfire. So that is a very obvious kind of application. For ESAC, okay, do we have some kind of a killer application? I mean, that is indeed okay. So let's compare with the AI and this SIGINT, okay, space air ground integration. We need to think about it. And on the other hand, okay, this AI with the ESAC is a kind of many kind of there may have many potentials, and also space air ground with this kind of ESAC can also have many potential to work. So basically, okay, I feel this two part can I mean, at least okay, there are still some research issue here. Okay, so this is our lab, and okay, so let me stop recording.